Today is day 20 of Advent of Cyber, and today's challenge is called Binwalking Around the Tree. We can now learn more about the mysterious device found in Santa's workshop. Elf Forensic McBluey has successfully been able to find the device ID. Now that we have the device ID, help Elf McSkitty reverse the encrypted firmware and find interesting endpoints for IoT exploitation. The learning objectives are: what is firmware reverse engineering, techniques for extracting code from firmware, extracting hidden keys from encrypted firmware, and modifying and rebuilding a firmware. Every embedded system, such as cameras, routers, smartwatches, etc., has pre-installed firmware, which has its own set of instructions running on the hardware's processor. It enables the hardware to communicate with other software running on the device. The firmware provides low-level control for the designer or developer to make changes at the root level. Reverse engineering is working way back through the code to figure out how it was built and what it does. Firmware reverse engineering is extracting the original code from the firmware binary file and verifying that the code does not carry out any malicious or unintended functionality, like undesired network communication calls. Firmware reverse is usually done for security reasons, to ensure the safe usage of devices that may have critical vulnerabilities leading to possible exploitation or data leakage. Consider a smartwatch whose firmware is programmed to send all incoming messages, emails, etc. to a specific IP address without any indication to the user. Firmware reversing steps. The firmware is first obtained from the vendor's website or extracted from the device to perform the analysis. The obtained or extracted firmware, usually a binary file, is first analyzed to figure out its type, bare metal or OS based. It is verified that the firmware is either encrypted or packed. The encrypted firmware is more challenging to analyze, as it usually needs a tricky workaround, such as reversing the previous non-encrypted release of the firmware or performing hardware attacks like side-channel attacks to fetch the encryption keys. Once the encrypted firmware is decrypted, different techniques and tools are used to perform reverse engineering based on a type. Firmware analysis is carried out through two techniques, static and dynamic. Static analysis involves an essential examination of the binary file contents, performing its reverse engineering, and reading the assembly instructions to understand the functionality. This is done through multiple commonly used command line utilities and binary analysis tools such as Binwalk, a firmware extraction tool that extracts code snippets inside any binary by searching for signatures against many standard binary file formats like zip, tar, exe, and elf. Binwalk has a database of binary header signatures against which the signature match is performed. The common objective of this tool is to extract a file system like SquashFS, YAFFS2, CramFS, XTFS, JFFS2, etc., which is embedded in the firmware binary. The file system has all the application code that will be running on the system. Firmware modkit is widely used for firmware reverse engineering. It extracts a firmware using Binwalk and outputs a directory with the firmware file system. Once the code is extracted, a developer can modify desired files and repack the binary file with a single command. Firmwalker searches through the extracted firmware file system for unique strings and directories like etc shadow, etc password, etc SSL, special keys like admin root password, vulnerable binaries like SSL, telnet, and netcat, etc. Firmware dynamic analysis involves running the firmware code on actual hardware and observing its behavior through emulation and hardware-software-based debugging. One of the significant advantages of dynamic analysis is to analyze unintended network communication for identifying data pilferage. The following tools are also commonly used for dynamic analysis. QEMU is a free and open source emulator and enables working in cross-platform environments. The tool provides various ways to emulate binary firmware for different architectures like advanced RISC machines, microprocessors without interlocked pipeline stages, etc. on the host system. QEMU can help in full system emulation or single binary emulation of ELF, executable in linkable format, files for the Linux system and many different platforms. GNU Debugger is a dynamic debugging tool for emulating a binary and inspecting its memory and registers. GDB also supports remote debugging commonly used during firmware reversing when the target binary runs on a separate host and reversing is carried out from a different host. Okay, so I'm going to launch the machine for this challenge and I'll be right back. Well, it ended up being longer than I thought it would be, but anyway, let's continue. After identifying the device ID, McSkitty extracted the encrypted firmware from the device. To reverse engineer it, she needs an unencrypted version of the firmware first. Luckily, she found it online. Open the terminal and run the dir command. You will see the following directories. We can go dir, I've got the directories there. The bin folder contains the firmware binary, while the firmware modkit folder contains a script for extracting and modifying the firmware. This exercise will primarily be using two tools. Binwalk for verifying encryption and can also be used to decrypt the firmware, binwalk-e-n, and firmware modkit, library for firmware extension and modification, extract-firmware.sh. So verifying the encryption. In this step, McSkitty will verify whether the binary, firmware v2.2-encrypted.gpg, is encrypted through file entry analysis. First, change the directory to bin folder by entering the command cd bin. She'll then use the binwalk tool to verify the encryption using the command binwalk-e-n and the file name. So we will cd into bin, and we'll do binwalk-e-n and firmware encrypted. So the result says rising entropy edge 0.989. So that means the file is probably encrypted and has increased randomness. Finding unencrypted older version. Since the latest version is encrypted, McSkitty found an older version of the same software. The version is located in bin unsigned folder. Why was she looking for an older version? Because she wants to find encryption keys that she may use to decrypt the original firmware and reverse engineer it. McSkitty has decided to use the famous FMK tool for this purpose. To extract the firmware, change the directory by entering the command cd ... and then cd bin unsigned. She extracted the firmware by using the following command: extract firmware sh and then the file name. So we'll go cd ... / and it is bin unsigned. Then we will use extract firmware.sh and we'll use on the file, run that. Okay, so it's asking for the password to continue running it. The password is capital S Santa 1010, so we'll type that in and enter it. Okay, so it's extracted the firmware into the FMK folder in the current directory. Finding encryption keys. The original firmware is GPG protected, which means that we need to find a public and private key and a passphrase to decrypt the original signed firmware. We know that the unencrypted firmware is extracted successfully and stored in the FMK folder. The easiest way to find the key is by using the grep command. The -i flag in the grep command ignores case sensitivity, while the -r operator recursively searches in the current directory and subdirectories. So what we can do is grep-ir key. So that will recursively go through the current directory, and looks like there are public and private keys right at the bottom here. Bingo, we have the public and private keys, but what about the passphrase usually used with the private key to decrypt a GPG encryption file? Let's find the passphrase through the grep command. Okay, so it's actually paraphrase in here, so we'll do grep-ir paraphrase, and that's found there, Santa at 2022. McSkitty has finally located public and private keys and the paraphrase as well, decrypting the encrypted firmware. Now that we have the keys, let's import them using the following command: gpg import and the private key. So let's do that. gpg-import, and that file is in fmk root fs gpg private key. So let's import that. So it wants us to add in the passphrase for it, which was Santa at 2022, and it's imported the key. While importing the private key, you'll be asked to enter the passphrase, which was found in step 3, and now let's import the public key. So that's gpg-import fmk root gpg public key. Okay, so that's now imported. Once the keys are imported, McSkitty decrypts the firmware using the gpg command. Again, change the directory by entering the cd command and then bin cd-bin. Now that we're inside that directory, we can do just gpg and the file. We'll put in the passphrase again, which is Santa at 2022. And if we look in the current directory, this, we have the file which is no longer .gpg, reversing the original encrypted firmware. This is the simplest step, and we can use binwalk or FMK to extract code from recently unencrypted firmware. In this example, we'll be using FMK to extract code. So use extract firmware and the file name. So extract firmware and the file, like so. So it's extracted it into the current directory of FMK. McSkitty has finally been able to reverse the complete firmware and extract essential files she'll use for the IoT exploitation. She has used the keys from an older version to decrypt the latest version of the same software. The camera folder in root fs directory will contain all the necessary files we will be using for the next task. So what is the flag value after reversing the file? Firmware version 2.3 encrypted. So as we learned before, we can use grep to do this. So grep-ir, and we can search for thm, and the flag is thm. We got the firmware code, so we can paste that in and submit. What is the passphrase value for binary? That was Santa at 2022. After reversing the encrypted firmware, can you find the build number for rootfs? So let's see if we can do another grep-ir and let's say build. So that wasn't exactly what we're looking for, but we can see in the directory it's 2.6.31. So 2.6.31, submit. And that is day 20 of Advent of Cyber completed. If you like this video, make sure to like and subscribe.